This problem is called the Atwood machine. It's very common in this section of physics here, and it's a pulley, a massless light pulley here with a massless light rope going over it, and each side of the rope has a mass attached to it. We'll have M1 on the left side and M2 on the right side. The goal of problems like this here are to find the acceleration of the system, so we'd like to know what the acceleration of it is, and we'd also like to know what the tension in the rope is. Typically, two things like that are either what the problem is going to be asking for, or if you have knowledge of those two things, you'd be able to solve for something else the problem might be asking for. So let's just get right at it. So in this particular problem here, these types of problems, we have a pretty strict recipe we're going to follow, which can often lead to a sort of productive session here and a productive answer. First thing we're going to do is we're going to recognize the X and Y versions of Newton's laws. Next thing we're going to do, we're going to identify the forces on all objects. We're going to set up a sign convention on the problem, and then we're just going to use this work here to fill in equations 1 and 2, and out will come our answer. So the first thing we'll do then is we'll start with step 3. We recognize 1 and 2 are our working equations. Go to step 3 here, and we're going to identify forces. So all the forces that I can see on this problem here is there's definitely a downwards weight on M2, and there's an upwards T on M2. T's always pull away from their points of contact. On M1 over here, there's definitely going to be a T pulling up on it like that. Again, tension pulling away from this point of contact, and there's definitely going to be an M1G, M1's weight pulling down on it. So I have identified all the forces on all objects in the problem, noting that this is the same light massless rope going over the pulley, so we'll have the same tension on both sides. I will not label this T1 and T2 because the tensions are the same. There's no reason to use two different variables when they're the same, and it cuts our work down some. Next thing I'm going to do is go on to step 4 here. Step 4 is involved identifying a sign convention for the problem, so I'll just go ahead and do that. We like to call down negative, so I'll go ahead and write the minus sign right there. And if down is negative over here, up must be positive over here. And like we said in some other video, tensions on ends of ropes, on opposite ends of a rope, have opposite signs. So this is a positive sign right here. That's going to be a negative sign right there. And if that's a negative sign going up, that means up for this mass is negative. That means down for this mass would have to be positive. So there's my sign convention. You can see how nice and consistent it is here, that if M2 moves down, it's moving in the negative direction. But because of the pulley in the rope, if M2 moves down, M1 must be moving up, and that would also be the negative direction for M1. And you should be able to talk yourself through the same sort of analysis if it was a positive motion. So in either case here, we've identified the forces, we've written down all the signs. Let's just fill in equations 1 and 2, and we should also add that we're going to fill in equations 1 and 2 for both objects. So we'll just start here for mass M1 here. So for M1 here, we'll fill in equation 1, which says that the x acceleration is the sum of the forces divided by m. So I look at M2 here and I don't see any x forces, so I would really like to fill in the sum of the x forces divided by m, but I don't see any x force on M2, so the equation just isn't going to help us. It's there, it's available, but there's no reason to use in this problem, so we won't worry about it. But now I do have the other one here, which says AY is the sum of the y forces divided by m. I do have that one available to me, so I can use that. So I'm going to fill in this force sum here. So it says AY is the sum of the y forces. So what I see on M1 right here, as I look at it, I see a tension up and a weight down. So I see a minus T plus an M1G over M1. There you go. So I filled in equation 2 there for that particular mass. I will continue the problem and do the same thing, but for the other mass, I'll put a box around this first because it's sort of an important equation. It is a key result for us here. I'm just going to stop with M1 for the moment and move on to mass M2. Now for M2, likewise for the other one, I look at M2, I don't see any x forces on M2, either any left or right forces, so although this equation is available to us and is valid, it just doesn't help us in this particular problem, so I'll move on to equation 2 there with the a sub y. So I'll go ahead and fill in that one there. A sub y now, if I look at this other mass here, M2, I see a plus T up and a minus M2G down. That's the sum of the forces. So I see a plus T minus M2G down over M2, and that's my equation for that mass. So you can put a box around that and say, well, doing just fine. Equation step number 5 says fill in 1 and 2. I've done that now, and indeed I almost have most of the solutions at hand. So the last thing you can sort of identify with here was covered in some other videos, but it's a little bit intuitive here. Seems like you have two accelerations, AY, which is which. Well, this is really the y acceleration for mass 1, and this is the y acceleration for mass 2. Are they the same or different or what? Well, we have some other discussion in another video that says when two objects are connected by the same rope, V and A for both of them will always be the same. So if whatever M2 does, M1 sort of has to follow because they're linked by the rope. So you can conclude correctly then that in this particular problem and many others like it here, that this acceleration right here and this acceleration right here will be the same because the masses are connected by the rope. So if they're the same, then you can do a couple things. You can just replace these with just an A and solve, or you can just equate the two equations, which is what I'll do to get our first answer to come out. So if they're the same accelerations, I'll just sort of equate the two things. So I get a minus t plus m1g over m1, and that'll all be equal to plus t minus m2g over m2. So you can get one big equation. You can put a box around that if you want, and we won't do this in this video here, but in principle, this can be solved for t. With some algebra here, you can just solve this for t straight up. Probably the first step is to multiply through by m1, second step multiply through by m2. In either case, you can get t. And once you have that t done, you get a bunch of stuff for t there. Once you have the t done, you can take the answer for t and plug it in either for this t or for that t, and what that'll do is it'll give you another equation solved for a. So this is really your first step here, and if you again take this t that you get and plug in either there or there for that t, you can get the acceleration. And I believe in this case here, the acceleration is going to come out to be m1 minus m2 over m1 plus m2 times g. That's what your acceleration would be. And it makes a bit of intuitive sense if you look at it. Think about it just for a minute. Suppose that m2 was the more massive block. That means this is the heavier block. Intuitively, you might think that if the Atwood machine started at rest, m2 would move down since it's the heavier block, and that's the negative direction. And the equation does seem to be consistent with that. If m2 is a larger block, this is going to be the larger number, and a smaller number minus a larger number is a negative. Positive on the bottom, positive 9.8 right there. So the acceleration would be negative. That indicates that the whole system will move in the negative direction, which is consistent with m2 being the bigger number. So here is one of your answers for you right here at the bottom. A is m1 minus m2 over m1 plus m2 times g. That is the acceleration of the system. The tension also pops up, and that's essentially the solution to the problem.